Okay, hello everyone. My name is Michael Downey, Library and Information Services Coordinator at the AWRI, and it's my pleasure to welcome you to today's webinar and also to welcome today's presenter, Dr. Tony Proffitt. Now, Tony works as a viticulturist for AHA Viticulture, Precision Viticulture Australia, based in the Margaret River region of Western Australia. He's also a lecturer in viticulture at Curtin University. And while he doesn't claim to be an expert in UAV or drone technology or remote sensing camera systems, but as a practicing viticulturist, recognises the need to be aware of emerging technologies that have many benefits in the vineyard. And today, Tony will share his thoughts on whether this technology offers grape growers opportunities and point out some of the things to be aware of. But before we go to Tony to elaborate more on these thoughts, a couple of notes on what you as the audience can expect. As always, the format is a short PowerPoint style presentation followed by a Q&A. The session is being recorded and will be available to view via the AWRI website. And finally, for those that are new to webinars, it's important to remember that webinars are interactive and there are a number of ways to get involved. To ask a question, please type into the question section of your control panel in the bottom right corner of your screen. And for those with access to a microphone, there is also the option of speaking directly with our presenter by clicking the raise hand button. This is located in the top left section of your control panel. If you prefer to ask a question via email, please do so at infoservices@awri.com.au. And please send through your questions at any time. And once we get to the Q&A, I'll forward as many questions through to Tony as possible. And finally, if you'd like to get involved through Twitter, please use the Twitter handle @_AWRI. Okay, that's enough from me for now. I'm now going to hand over to Tony to tell us more about today's topic.
Obviously, UAVs or drones have been getting a lot of press in recent times, and I'm aware that there's an increasing number of operators offering a range of services. As Michael indicated, I don't claim to be an expert in the technology or the remote sensing camera systems per se, and nor do I have a license to operate a UAV. But the project that I'm going to refer to briefly in this presentation came about because I was getting a lot of questions about drones and UAVs, unmanned aerial vehicles, from growers, and I felt that I needed to be a bit more informed so that I could pass this information on. So I'm going to begin this presentation with a recap on what remote sensing is all about in relation to agriculture and viticulture applications, and talk about the various platforms that can be used to acquire or capture reflectance data. I think this is important to go back to recap on this so that we have a good understanding when thinking about buying a UAV or using a service provider for remote sensing applications. I'll then look at some of the characteristics of UAVs and the camera systems that they carry, and show some examples of imagery acquired last season by aircraft and a fixed wing UAV. What other opportunities are there for UAVs and vineyards apart from remote sensing? I think that's a question we all need to have a think about. I will discuss and refer to a couple of potential applications that I've considered, and no doubt you may have other ideas and thoughts on this. And then I'll finish off by a brief mention of the regulatory side of operating a UAV, and also provide some ballpark figures, ballpark costs for actually purchasing imagery if you don't already do that, or you're not aware of the sort of typical costs. So we'll all be aware that land is inherently variable, as this photo of a vineyard illustrates. Through the development of a range of spatially enabled technologies, which we refer to as precision viticulture, grape growers and wine producers, can now able to map the spatial variability in the performance of their vines. They can map the differences in soil characteristics and also collect landscape elevation across their vineyards. One of those cost-effective tools that growers have found to be useful is to assess the variability of vine in assessing the variability in vine performance is actually through remote sensing. And there's numerous examples out there in the industry that will demonstrate this, and no doubt, well, I know some of the people who are listening in already use remote sensing imagery acquired by aircraft and to some extent satellite for doing that. But I'd like to, as I said, go through remote sensing again, so to remind some people who are not perhaps familiar with the technology. So the simplest form of digital imaging system used today is the multispectral system, which allows more than one wavelength of the light spectrum to be recorded as an individual color component. So generally there are 4 separate narrowband sensors, and I'll use the word narrowband because we'll talk about narrowband and wideband a bit later. So narrowband sensors, which are used to detect the reflected light in the blue, green, red and near infrared wavelengths. So as you can see in the diagram, these wavelengths span the visible light range from 400 to 600 nanometers to the infrared range 690 to 900 nanometers. And it's this area of the spectrum which is of particular interest to us because this is where the strong contrast, where there is strong contrast between the vine and non-vine material, which I'll demonstrate in this slide. So we've got sensors or cameras detecting and recording the sunlight from the surface of targets on the ground. So in this figure we can see that we've got reflectance profiles for some Cabernet Sauvignon vines, a chickpea cover crop and some bare soil. And we can see that there's a large difference in the spectral reflectance from these 3 targets, particularly in this near infrared waveband. So in this section here we see a separation between those in those targets. So healthy, vigorous vine biomass exhibits strong near infrared reflectance and a low red reflectance, which is why the reflectance data in the near infrared wavelength is in particular important to capture. So assuming that we have 4 sensors capturing reflectance data, we can produce a true color image, and those who get imagery from a service provider may receive a true color image, and that's collected from the blue wavelength, the green wavelength and the red wavelength. And the green color in the image below represents vines, representing vines differs in patches according to the vigor. So the darker the color, the greater the vine biomass. Alternatively, we can use the green, red and near infrared wavelength to create what is called a false color imagery. And again, those who get imagery from a service provider may receive imagery in this format. And again, it shows differences in vine biomass, with the deeper red representing more biomass than the lighter red. And in this case, we've got some bare soil and dead grass around the perimeter of the vineyard, and that appears as blue-green. Reflectance data can be transformed into a single number, or what we call a vegetation index, at each pixel. And we know from many vegetation studies that this is related to vine biomass or plant biomass, and in particular the photosynthetically active biomass And we know from ground truthing that this is correlated to what we see on the ground in terms of vine canopy size and health. So this is particularly useful index. There are a number of indices used in vegetation work, but in Australian vineyards, the plant cell density index has become popular and has been found to correlate well with what we see on the ground. So this is our preferred index to use. It's derived by dividing the near infrared reflectance by the red reflectance value. And from that, we can then generate a map, such as the one below, of plant cell density values. And they, in turn, can be grouped into a number of classes. Generally, we use 3, and the standard now is to use a grading from red through to blue, with red being the lowest plant cell density values, to high being the blue. Okay, so let's have a bit of a look at spatial resolution. So this term refers to, is a measure of the smallest object detectable on the ground. It's determined by pixel size, which is determined by the megapixel capability of the sensor, and the distance between the sensor and the actual target, whether that's vegetation or soils. So as depicted in this diagram, the closer the sensor is to the target, the smaller the overall image coverage and the greater the image detail. So in commercial Australian vineyards, reflectance data is generally acquired using light aircraft, and imagery is delivered with an on-the-ground resolution of 0.5 metre. And that seems to work well for our particular planting densities. It provides sufficient detail at an optimal cost to allow the vine and non-vine information to be separated out when processing the data. So, as you'll appreciate, it's important to remove as much non-vine data as we can if we are interested in looking at the vine canopy characteristics. So if you receive some data, you've got a service provider providing information about your vine canopy, then you need to be ensured that the non-vine material, the soils, the cover crops, weeds perhaps growing underneath the vines, have been removed from that data set. So what you see and what you get is only the vine canopy. So as the pixel size increases to become similar to the mid-row spacing, there's going to be an increasing mix of vine and non-vine information. So say over time, the industry has worked out that about 0.5 metre resolution is a good compromise to allow sufficient non-vine material to be taken out that's useful. But of course, we can have a much higher resolutions than that, both from aircraft, but particularly now that we've got the use of UAVs, which obviously can fly at a lot lower altitudes and therefore can collect information at a much higher resolution. So now that we've been through Remote Sensing 101, let's turn our attention to how the reflectance data is captured. So as I mentioned before, we've generally done this through the use of satellites and light aircraft, and now we've got the UAV as another potential platform. As you can see in the top figure, there are differences in the amount of detail and the level of coverage provided by each of these platforms. So satellites obviously operate hundreds of kilometers above the Earth. The highest spatial resolution currently available, as I understand it, is 1.2 meters per pixel, so 120 centimeters, which is provided by the World View satellite. Within the industry, the use of satellites as a platform is less popular than aircraft, and also in other agricultural applications for a number of reasons. One is that it's a lower resolution, it's got limited operational flexibility, and if you want to acquire imagery, they have to be programmed to visit your area. And there's also a requirement to purchase large areas in a single image. So I believe that the minimum is about 100 square kilometers. And lastly, there's a high risk of acquiring poor quality data due to cloud cover. As an example, we can see that in the diagram here. So light aircraft, that's what we generally use. They fly anywhere between 600 and 1700 meters. As I said before, the standard now is 50 centimeter resolution in vineyards, but certainly some service provider, the most common one for collecting or acquiring imagery around Australia is Specterra Services. They can collect imagery at 10 centimeters or 0.1 meter, so 10 centimeter is possible, but of course that will come at an extra additional cost. They have what I'd consider as moderate flexibility. Obviously there's a cost to put a plane in the sky, and there's also weather conditions to think about. There are some regions, for instance, where Specterra do have problems in collecting imagery at the right time. Mornington Peninsula, for instance, is somewhere that we often have cloud cover. The Hunter Valley can be a bit difficult due to cloud. We generally collect imagery once per season, and that's around veraison time. Now also we've got UAVs. Now, as everybody would appreciate, they are remotely piloted aircraft that can be operated from the ground. They can be operated either fully or semi-autonomously according to pre-programmed flight plans. Historically, they've been used by the military, but in recent years they've become popular and affordable for civilian use. So, for example, they're used now in firefighting, surveillance, search and rescue, surveying, covering sporting events, that sort of thing. So there are two main models, either fixed wing or rotary wing. They can fly just above the canopy or up to the regulation imposed altitude of 120 meters. So that's a regulation imposed by CASA. Depending on the equipment on board, they can acquire imagery up to about a centimeter resolution, so 0.01 meters per pixel. And an important characteristic is that they are obviously very flexible in terms of flight scheduling and the frequency of flights, compared with either of the other two platforms that we've just been discussing. So the fixed wing, they obviously come in a range of sizes. They come with a couple of launching options, either by hand or by catapult. They're usually used for areas in the order of 200 hectares, roughly. Again, they have a range of about 2 kilometers, but there are line of sight restrictions, which we'll talk about in a bit later on when I talk about regulations. They fly at relatively high speeds of about 75 kilometers an hour. In terms of duration, it's very variable. It very much depends on the payload, in other words, what they're carrying, wind, and the battery configuration, but it can be anywhere between, say, 20 minutes and up to an hour and a half. Certainly wind has a big impact in terms of their efficiency, so generally they shouldn't be used in wind speeds of much more than about 40 kilometers an hour. They also require a flat area for landing, and I've put eagle magnets. I've seen a couple of demonstrations of fixed wing in the sky in the Margaret River region, which is surrounded, many vineyards surrounded by trees, many of which are habited by eagles, and certainly if you've got a dogfight going on in the sky, I would suggest that the eagle is going to win, and that you may find that you've got quite a hefty UAV bill after such a confrontation. So a couple of photos here. The top left is a UAV fixed wing that a service provider uses, that's been assembled from component parts. A launch by catapult in the photo below, and the UAV coming in to land. And I have got a short video clip of this, so if we have time I'll be very happy to show that. On the right hand side we've got a commercial UAV which you can buy off the shelf. This is called the EB. Again, this is being launched, but launched by hand in this particular case. Both are semi-autonomous and need to be controlled to take off and when landing, and using the control box that you see on the bottom right hand corner. Then we have the rotary wing models. There are a whole range of options in terms of what the main rotors look like, what the tail rotors look like. Most have vertical takeoff and landing capability. They are usually used for smaller areas, maybe in the order of 100 hectares or less usually. They have a shorter range. Flight duration, again, will vary on payload and the wind and the battery, but is less than the fixed wing and can be in the order of 15 minutes. It may be a little bit longer, it could be shorter. Compared with fixed wing, they have a greater maneuverability. They can hover above a target and can therefore acquire imagery at greater resolution, and can acquire imagery at oblique angles as well as just vertical angles. So here we have a UAV flying above a vineyard, and you can see that there's a camera mounted, a compact camera mounted, and in this particular case you can see it's taking oblique imagery as opposed to vertical imagery. So let's just turn our attention to the payload in terms of what it's carrying for remote sensing applications. So as I indicated before, there are numerous types of remote sensing digital imaging systems available. And obviously we want to acquire quality imagery that's going to be useful in the vineyard. And if we're going to do that, we really need to be thinking about using narrow spectral band sensors, so the multispectral cameras. Because UAVs have a weight restriction, and the greater the weight, that's going to affect the flight duration, multispectral cameras have become miniaturized, and as a consequence of that, they're good multispectral camera which can be used on a UAV is certainly very expensive. This has resulted in off-the-shelf cameras becoming popular due to their low cost on weight, their durability and compact size. The main problem with many of these is that the wavebands are not well defined, and So in other words, we can get some contamination of the information by capturing reflectance data outside those wavebands we're actually interested in. So in some cases, in many cases in fact, those compact cameras may not even have a near infrared waveband, and the camera has to be modified to be able to, if some can be modified to incorporate one. And we saw earlier on that I mentioned why it's important to have that near infrared waveband available for mapping vegetation. Also, we need to be aware of that some cameras operate in a mode that automatically adjusts for changing light conditions. In this mode, images are going to change from shot to shot, which therefore makes the data useless for determining variability in canopy characteristics. So if there is a facility to turn that mode off, then that is certainly necessary. So here's a couple of photos of a multispectral camera. This is the Mica Sense. Used this in the trial last season. So this was on board a fixed-wing aircraft. You can see the underneath of the UAV 5 cameras, in the camera lenses in this case. We've got the blue, the green, the red, the near infrared, and the fifth is actually what's called the red edge waveband, which is a waveband within the spectrum of 690 to 730 nanometers. There's been quite a lot of interest in this particular waveband because it's been found to provide additional information about vegetation characteristics. So that's what the red edge, if you ever read anything about it or come across it. On the right-hand side, there's what I'd call off-the-shelf camera. It's a compact camera with a single lens, as you can see below here, which is very much like the compact cameras that we're all familiar with and probably use. I want to mention here about a one-year extension project funded by AWRI last season under their regional program. As I mentioned before, I was getting quite a lot of inquiries from growers about UAVs and whether they were useful in the vineyard for collecting remote sensing data, reflectance data. So as part of this project, reflectance data was acquired and processed by Specterra Services using their conventional light aircraft and multispectral camera system. These, as I mentioned before, these are the guys that generally acquire imagery for growers around in most regions across Australia. Also, the collected reflectance data using a fixed-wing UAV by a company called Global Unmanned Systems based in Perth, and the trial site was at Cape Mantell in the Margaret River region. Imagery was acquired close to Veraison, so for this region that's in mid-January. The cameras had similar capability, but obviously miniaturized in size for the UAV. Data was acquired at a higher resolution by the UAV because of its ability to fly at low to altitude. So we ended up with a spatial resolution of 50 centimetre for the conventional aircraft as per normal versus 11 centimetre resolution acquired by the fixed-wing UAV. In the top diagram here, we have some plant cell density values collected by the aircraft at that, say, the standard 50 centimetre pixel resolution. And below it, we have the same area of vineyard collected by the UAV at a higher resolution. If you may be able to, when looking at these, you may be able to see that there is a pretty good correlation between what you can see in terms of the spatial distribution of plant cell density values along the rows. So as we look along the rows here, it's quite similar to what we're seeing along the row in the UAV imagery. The higher resolution collected by the UAV, if you look here, you can actually see that there are some differences. You're able to pick up differences in the plant cell density or the vigor of the vines in a perpendicular fashion. So you can see this generally on the edges of the vines, it's red, in the center of the vines. It's blue, showing really that there's greater density in the middle of the canopy compared with as moving out towards the periphery of the canopy, as we probably would expect. If you actually look at the stats, there's a poor statistical correlation. That's not surprising for a number of reasons. There's a much greater noise in the larger UAV data set. Remembering that there's quite a significant difference in pixel size. So we've got about 25 UAV pixels within every aircraft pixel. The other reason that there's likely to be a poor correlation is the fact that the data was not acquired on exactly the same day at exactly the same time of day. So there are always, the way that remote sensing works is that there will be some differences in it's affected by shadows, and which is obviously affected by cloud cover and the time of day where the sun is positioned. So unless you collected the imagery exactly at the same time, then there obviously is going to be some differences. So we're really not comparing apples with apples in this particular case. But that doesn't necessarily matter. What I want to show here is that this slide shows the UAV PCD values shown with the usual red to blue scale in here, superimposed onto an aircraft 50 centimeter pixel, which is shown in grey. And if you actually want to have a look at magnified area, I've magnified that here. So we can actually see here that the PCD values on the edge of the canopy versus the PCD values in the center of the canopy, superimposed onto one pixel of the aircraft. Earlier on I mentioned the importance of removing non-vine information so that we only have plant cell density values relating to the vine canopy biomass. So obviously at the higher spatial resolution it is certainly possible to remove more of the row shadow and inter-row pixels than at lower resolutions, and therefore we could provide a better definition of the vine only pixel because you've got greater detail. But this comes at a cost in terms of data processing, and in the end of the day we have to ask ourselves the question, does it make any difference in the way that we're going to zone up our vineyard or manage our vineyard? So there's a couple of examples for you. The UAV data has been smoothed to the same 50 centimeter pixels, so we're actually they're actually comparable. The two sets of images are now comparable. It still means that we collected the data at 11 centimeters resolution for the UAV, but they've been smoothed to 50 centimeters, so you can compare them. I should point out that the way that the data interpolation was used for the UAV was the inverse distance weighting method. I don't know what Specterra used, the way that Specterra do that, and that's confidential information. It could be that the two techniques are slightly different, in which case this may result in some inaccuracy in comparing one set of data with another set of data. But in the end of the day, we don't the exercise isn't necessarily to compare one data set with the other data set. It's to look at the spatial distribution of the plant cell density values. So I think you would agree that even though the UAV is slightly more pixelated, and there's data processing reasons why that might be, but we can see that the spatial distribution of plant cell density values is, generally speaking, pretty similar. Yes, there's an area up here that seems to be a little bit different compared with the aircraft. and whether that's real or not is unknown. Again, another block of Cabernet, again, pretty similar distribution in canopy vigor across the vineyard. Perhaps a little bit of a difference in here, and again, it wasn't ground truth, so I'm not sure whether this is real or whether this greater detail collected from the UAV is picking up something that the aircraft didn't. In the end of the day, would we manage this block of vines any differently from this block of vines had we using a UAV versus the aircraft outputs? Okay, so that's remote sensing, and we can come back to that in a little while, but of course there are other potential applications for UAVs in vineyards. I think perhaps there's a question mark about the benefits of using them for remote sensing work, unless we want to acquire data several times throughout the growing season. But what other applications could we use it for? Well, certainly digital elevation or creation of topographical models using this ultra-high, rather than high, but ultra-high resolution data, and surveying companies are certainly using UAVs for this very purpose. It's quicker, they're quicker, or using this technology is quicker than doing on-ground surveys for the same or even better accuracy. They don't, if you want to use them in this way, they don't necessarily need expensive multispectral camera systems to do this. And of course there are a number of things that we might use topographical models for in our vineyards, for modelling air drainage or water movement, soil erosion, designing irrigation, drainage infrastructure, positioning soil moisture monitoring equipment, positioning frost fans, etc. So there's a number of reasons why getting a topographical information about our vineyards is useful. And if we can do that quicker and easier and more accurately using UAVs, then yes, there's a use for them. Possibly for surveillance, tracking the movement of animals, vehicles, people, etc. A bird's eye view can be achieved by a person operating a UAV if there's another, and also having another person viewing and recording that imagery on a smartphone or tablet, if that's something that we feel that's useful. Oblique and vertical imagery certainly can be acquired using the rotary wing models. Certainly, you know, there's some data processing issues for oblique imagery, but there might be some useful things there. Improving the way that we perhaps estimate crop yield or do our monitoring, so phenology, early detection of pests and diseases, for instance. Certainly in France, I believe that they are looking at monitoring flavescence doré, phytoplasma, using this technology. The grains industry is evaluating the early detection of Russian wheat aphid. They're also looking at using them for detecting stripe rust in wheat. Temperature-based applications using thermal infrared sensors. They're currently expensive, they have low resolution output, but even with what we have right now in terms of current technology, we could use them for detecting irrigation leaks by detecting relatively cool and warm patches associated with wet and dry soils. They can't really be used for assessing plant water status, as I understand it at this moment in time, but that's going to change, and if that happens, then I think there's some opportunities to use them for irrigation scheduling applications. As a Queensland company, using them for dispersing predatory insects in horticulture. Possibly, certainly in the southwest, we have a bird issue. This Dutch company is developing bird-like UAVs for bird scaring. No idea whether they'd work. Possibly they would. There's UAVs used for mustering sheep using air horns. Perhaps that could be used in some way, perhaps for bird management. Quickly, just having a look at UAV regulation. Australia is the first country to regulate. If you want more information, have a look at the CASA website. It gives you details about operator certificate, remote pilot certificate and controller certificate, all of which you need. These regulations are being reviewed at the moment, and it's possible that UAVs with a gross weight of 2 kilos or less will no longer require a license when used commercially. Operators, there is a 120-meter regulation imposed. Operators in unpopulated areas flying at altitudes less than that with approval from landowners may not require all 3 certificates. But we do need to be aware of certain rules, such as distance from airports. I think it's 4 nautical miles. From people, 30 meters I think is the number, and obstructions. And importantly, there's also needs to be have line of sight between the UAV and the operator. Just in terms of costs, the capital cost for UAVs is very variable, depends on the model and the size, the payload, the software, etc. Don't forget that there's an operating cost for UAVs. You've got to consider time to acquire and process the data if it's something you can do yourself. Certainly some training costs, licensing costs, and generally there will be some repair costs. Some costs for going back to remote sensing. If that's something that you're interested in, then these are the typical costs to acquire imagery, which includes data acquisition, the data processing and delivery. Anywhere between $32 per square kilometre to $65 on the satellite, depending on the satellite and the resolution. Aircraft, generally about $35 a hectare to $45 a hectare at 0.5 metre resolution. UAVs, it's probably too early. Really, there are only a limited number of service providers at the moment, so I suspect that prices will come down as more operators get closer to where you're located. But it seems to be in the order of anywhere between $25 a hectare to $40, but those could vary quite substantially. So just to sum up, I've just put together a table here, comparative characteristics for different remote sensing platforms that I have developed just based on my knowledge. There's 5 attributes. The first 5 attributes focus on data acquisition, while the 2 following attributes focus more on data processing. So UAVs certainly can operate closer to the target. They're more flexible in terms of scheduling, not dependent on cloud, but they have a shorter range, can cover only small areas at any one flying time, and may have lower reliability than aircraft at the moment. Spatial structure in canopy characteristics was similar between the 2 platforms used, and of course that's not surprising, and there should be if the appropriate sensors and data processing techniques are used. Greater accuracy can certainly be achieved at higher resolution because a greater proportion of the non-vine pixels can be removed during the data processing, but does this really improved accuracy translate into improved targeted or zonal management practices that provide cost-effective benefits? I think the main benefit of the UAV platform is that data can be acquired in near real time or on demand for detecting changes in canopy size or health throughout the growing season and perhaps exploiting limited windows of opportunity. What are the other tasks that we might want to do? What are the tasks that we can't already do with the existing technology? Once we have the answer to that question, maybe we can determine whether the UAV is the appropriate platform to use. But certainly, I think mapping vineyard topography, the early detection of pests and diseases, where there's some research going on, perhaps dispensing predatory insect surveillance, bird scaring, detecting vine water stress, detecting irrigation leaks have opportunities. And finally, operating UAVs does require many skills which incur a cost. So you need to think about flight planning, data capture, processing, interpretation if you're going to thinking about purchasing a UAV yourself. I've just put here a couple of recent articles on UAVs which you may be familiar with. I've also there are many scientific papers on the use of UAVs for remote sensing. I've just listed a couple of here which might be of interest. And if you're interested in more about remote sensing per se as a technology, then there's a couple of references at the bottom there under precision viticulture, precision agriculture that might be useful. And finally, I'd just like to acknowledge the funding through AWRI regional program, the project administrators, Global Unmanned Systems Spectator Services, and Cape Mantel Wines as the trial site provider. And happy to leave it there because I know time's getting on. If we have time, I've got a short little video clip that I can show, but we'll see how time goes. Over to you, Michael.
Thanks very much for that, Tony. Very informative. We'll move through to a Q&A now, but in the meantime, happy for you to go ahead and play that video while I just remind people how they can ask a question, Tony. If you want to get that started now, that would be good. So yeah, just a quick reminder, if you want to ask a question, please type into the questions section of your control panel or click the raise hand button.
So I might, is that too noisy?
No, that's fine.
So this, this is at Cape Mantel last season, Global Unmanned Systems using their UAV. You can see it is launched with a catapult. This has got the microsense camera on board, which is a high quality multispectral camera system. It's being launched. This is now coming in as a reminder, as I mentioned before, you need a flat area for the aircraft to come in. So yeah, that's pretty much it. I've got a very short little one of a GoPro camera on board a drone, just flying across a vineyard. This is more surveillance, I suspect. I'm not sure whether that's useful, but just as another way of capturing information using a UAV, if that's useful to people. So we'll leave it there, Michael.
Thanks for that, Tony. Got a couple of questions here. I'm just sending them through to you now. Are you able to pull them up, Tony?
Trying to. Oh yes. Okay. So I've got one question here. I would love to know more about the potential capabilities of UAVs and the associated software to aid in yield estimation. Is there already the capability to count inflorescence numbers, early season vines, early on in the season? I would suggest no. I would think not at the moment. I know that there's some project work that is going on using imaging technology based on the ground on a more of an on-ground robot, and I've seen data where bunches are being able to be detected using that system. It's never been tried on using UAVs. I guess there's no reason why it couldn't be, but I think we'd need to see how this AWRI-funded work in this country, and it's also happening in the US, goes from collecting information from the ground first using the associated imaging software. So it's not been used on aircraft as yet, and I think let's wait to see what the robots come up with from work that's been done in this country and in the US first. Is there a second one?
Just sent you through a second question there, Tony. More a comment really than a question from Todd.
Okay. Todd, okay, really great presentation, many thanks. Just wanted to let you know that we're intending to run a trial this vintage with UAVs capturing NDVI imagery 4 to 5 times throughout the season to determine whether we can capture imagery that allows us to influence the outcome of the vineyard rather than looking backwards and using such imagery to assist with the next season. Okay, great. Todd, we need to keep in contact. I'd like to hear how you go. This is through Treasury Wine Estates. Okay. What's your experience? Okay, from Aaron. What's your experience in using UAVs for bird management? None. I've not come across anybody using them for bird management. As I say, there is a Dutch company producing one that UAV that apparently look well. If you look at their website, they're producing these so they look like birds. Whether that has any influence in deterring birds, I have no idea. And there is certainly a local person looking at using air horns for bird management. But at the end of the day, you just have to remember that someone has to drive this UAV. So if you think that that's useful and that you can afford to have someone out in the vineyard controlling the UAV, that's fine. But I would suggest that that's quite an expensive cost. Certainly if that person is going to be out there for a number of hours. So I don't know about them for bird management. If they can be autonomous and set off at a certain time and be up there without a person controlling them, yes, I can see that perhaps there's a use for them, but at this moment in time the regulations wouldn't allow that, so I'm not sure how useful they would be for birds. Todd, again, have you guys looked at such temporal capture? No, we haven't. Todd, maybe you and I can talk about what you're intending to do at some stage, because I'd be interested. But no, we haven't looked at temporal capture. The funding that we had just didn't lend itself to that, and nor did it lend itself to doing any on-the-ground work, which would actually be really nice, because obviously the next stage would be to look at the imagery collected by UAV and do some monitoring on the ground, and that might be just in terms of canopy biomass, but ideally it would be interesting to see if it can pick up any diseases such as powdery, for instance, or any insect pests. So if we did actually know, if we had a section of a vineyard with and without a pest and a disease, then that would be quite interesting to see whether that can be picked up. But again, it's a it's a significant research project which we weren't able to do in this last season. Another question from Peter O'Reilly. Tony, is the GoPro and light rotor UAV a viable option for gathering PCD info? So the answer to that is no. So the GoPro does not have it hasn't got an ability to collect imagery in the wavelengths, narrowband wavelengths that we require for producing plant cell density. So no. Peter O'Reilly again. USQ and UNE are collaborating on a project at Stanthorpe using UAVs and ground-based imagery to predict yield from Verizon bunch data. Okay, good. So there's obviously quite a lot of interest in using UAVs for detecting bunches. The more that people can get some projects happening, the better in terms of seeing where this technology fits. Jim, over in New Zealand, is there potential to identify pests and diseases, especially powdery mildew outbreaks or hotspots within blocks? Don't know, Jim. As just mentioned before, that work hasn't been done in viticulture. Certainly the grains industry is being supported by Grains Research Development Corporation to look at the early detection of pests and diseases in wheat. So there's a very significant program going on in that regard in Australia, based at the main centre in Perth. So we haven't done that in grapevines. I suspect we should be looking over their shoulder and see what they come up with. But as I said earlier on in relation to Peter's question, I think it would be really good if anybody is using a UAV at very high resolution with the appropriate sensors in the foreseeable future, say this season coming, if we can collect that imagery and have some powdery mildew, for instance, in a section of the block, that would be really interesting to see if there's any way of detecting that. Jim, I know there is a girl in Hawke's Bay, New Zealand, who is doing work with UAVs in a bird scaring manner. They work and are an alternate option to shotguns, quad bikes, racing around vineyards. That's great, Jim. I don't know who that is, but I'd love to know more. And I think this is a fantastic forum for people to know who's doing what and getting other people's experience. So obviously I wouldn't know about the work that's going on in Hawke's Bay doing that, but I'd really like to know a bit more about it and hear how that's working. Now, I don't know whether that's you may be able to find out whether it requires somebody being on site all the time operating, or whether they can use UAVs autonomously without someone being on site, which there may be slightly different New Zealand regulations than there are in Australia.
That's all we have with regard to the questions for now there, Tony. Before we start to wrap up,
yeah.
Did you have anything you wanted to add before we finish up? I have just got one further question. I'll just send it through to you, but if you do want to make any final comments, that's fine.
No, not really. I guess just to sum up, really, the technology is obviously in its infancy. I think as it matures, costs are going to get cheaper, and I'm sure there'll be more service providers. As a remote sensing platform, I'm not convinced that it's a useful tool to use unless somebody wants to monitor vine growth, and it's certainly possible. I think there's some work going on looking at being able to derive leaf area index using UAVs at those high resolutions. If we want to have a look at the change in canopy throughout the whole growing season, then obviously this is a fantastic platform to be able to use to do that. But if we're happy to make decisions and manage vineyards based on one set of data collected at Verizon, then I think the aircraft is the best platform to use. Again, but if you're in an area where there's low cloud and those sort of issues, then yes, there may well be some applications for the UAV from a remote sensing point of view. I guess if you're thinking of using a UAV service provider, my advice is that check what imaging system they intend to use. How is the data going to be processed, and how is it going to be delivered to you? So very much ask those questions, certainly about the imaging system on board, because as I hope I've demonstrated, there is certainly some issues associated with perhaps the cheaper compact cameras in terms of the data that you get from you will get some data, but whether it's of sufficient quality to make significant management decisions, I suggest it probably isn't. And I guess as an industry we need to think about what are these other tasks that we would like to perform, and if it's things like monitoring or early detection of pests and diseases, bird scaring, and estimating crop yield, then I think there's some great opportunities in terms of those applications. But I think we need to do some research. This wasn't a research project as such, but we need to be looking for some research funding to look at that, and also being in contact with others around the world who are doing this work. There's quite a lot of work going on in Europe using UAVs, certainly for canopy work, probably less so in terms of disease detection. So I think in that regards we should be looking at other industries such as the grains industry and seeing what they come up with. Final question here from Prue. For vine improvement source blocks, we need to survey for virus-affected vines, so we would welcome this technology. Yes, I agree, Prue. If we can pick up viruses, disease, that would be fantastic. And certainly, where we've got larger areas that we can't get around, obviously in smaller areas, I think we can still rely on our eyes and testing, but certainly on large areas, I think it'd be a welcome technology if we can do that. But the work hasn't been done, and if we think this is important, then we should be getting some funding to do this work. Peter O'Reilly again. Tony, we tried bird scaring this year and found it largely ineffectual. So, okay, some feedback from Peter there, which obviously is different from the Hawke's Bay example. Okay. So I don't think there's any more questions.
No, that's all we've got with regard to the questions. So I think we'll wrap it up if you're happy to finish.
Yes.
There, Tony?
Yeah. Yes, happy.
Okay, great. So yes, just to start with, a big thank you to Tony for agreeing to present. Some really informative information there, a great Q&A. Thank you to all the attendees also participated. For attendees, you will receive a follow-up email with a link to this recording. It'll also include a link to a survey. Should you need to follow up on anything, please feel free to contact the AWRI directly, and if need be, we'll put you in contact with Tony. Tony also flagged a few research articles in his presentation. If you'd like to get hold of any of these, please contact the AWRI library. Next week's webinar is from Paul Petrie at the AWRI, and will be on vineyard frost management strategies. If you haven't already registered for this session and would like to do so, please visit the AWRI website. And just finally, Once again, thanks to everyone for joining, and please check out the AWRI's webinar program to register for future sessions.